So for the 50th time, I've started a video and didn't like what I said. So let me start again. The first 12 problems are repeats, I think from section 6.4. These are exponential equations. They're exponential equations because there's an x in an exponent. And these equations are set up so they can be solved using prime factor trees. So to get started for these, I'm going to do a prime factor tree for any number that's not prime. And so in problem 2, the only number that's not prime is 27. 27 I can write as 3 times 9. 3 is prime, so I circle it. 9 isn't prime, so I make a branch off of it. 9 is 3 times 3. Both the 3's are prime. 27 is 3 times 3 times 3. This is the most simple kind of problem that we can do in this grouping from 1 to 12. I did a prime factor tree for any number that's not prime, and then this should, after this first step, I should now have each side written with the same base. I may have a parentheses to deal with as we get more complicated. But once I can get both sides written with the same base, in this case the bases are 3, the next step is to just drop the bases and set the exponents equal to each other. And then usually when I do this, I have to solve what's left, and then I'm going to have to check. There's maybe more going on in the solving that I haven't listed here because, like I said, there might be some parentheses to deal with, but not at first. For number 2, I did the prime factor tree for 27. That's a non-prime number. 3 is prime. I didn't need to do a prime factor tree. Now I have both sides written with the same bases, so I set the exponents equal to each other. Usually the exponent's a little more complicated and I'd have to do some algebra to isolate the x. That's by the solve step. But here, I think this is my answer. And I'm just going to calculator check. So the checking for number 2 would be to take the answer 3, plug it in for the x on the left-hand side, and make sure that the left and right-hand side equal each other. So clear this out. 3 exponent 3, that's the left-hand side. Well, 3 exponent 3, and that's equal to 27, so this checks perfectly. I'm going to get my other calculator out because this one's not showing up so well. So same thing for all the problems between 1 and 12. I'm going to do a prime factor tree for any number that's not prime. In problem 4, 3 is prime. I don't need to do a prime factor tree for it. 81 isn't prime, so I'll do a prime factor tree. 81 is 9 times 9. There are multiple ways to do the prime factor tree. They all lead to the same prime factoring. Here, 81 is going to be 3 to the 4th power. If you had before another class and you own this calculator, if your calculator's in mode 1, you could do prime factor trees by just typing the number that you want to do the prime factoring for, hit equal so you get the number in the upper left and the bottom right corner. So I typed 81, hit equals, then I hit my shift key, followed by this degrees minute second key or the quotes key, and it tells me that 81 is 3 to the 4th. It saves a heck of a lot of time. Anyways, for problem 4 now, I have this ability to write this as 3 to the x plus 2 equals 3 to the 4th. So now I have each side written with the same base. I should now have each side written with the same base. So now I can drop the bases and set the exponents equal to each other. And step 3, solve. I'm just going to minus 2 from both sides. This is going to give me x equal to 2 for an answer. Now I'll go on to the checking part of this To check this, I should go to the x in the original problem, change the x in the original problem to 2, and make sure I'm left with a true statement. So make sure that 3, when I raise it to the 2 plus 2 power, I get 81. On my older calculator that shows up better with this lighting, I have to put the exponent in a parentheses because it doesn't raise the exponent for me. And it checks just fine. There's a handful of tricks. One of the tricks that we learned a few sections ago is that if we had fractions, we need to make the fraction into a negative exponent. So in problem 6, I have to rewrite the left-hand side. The left-hand side right now is 1 over 3 to the first power, and I'm going to use the rule that if I have a fraction with a 1 in the numerator and a base to an exponent in the denominator, I can rewrite that with a negative exponent. So I can rewrite 1/3 to the x power as 3 to the negative 1 to the x power. 27, I think that's the same prime factoring that I did already. 27 is just 3 cubed. 27 is 3 times 9. And 9 is 3 times 3. So I can rewrite this as ultimately 3 to the negative 1 to the x equals to 3 cubed. Here I need to multiply the exponents. This is the one big trick in this grouping of problems before I drop the bases. So I can't have a parentheses on either side before I drop the bases. Now I have both sides with the same exponent. I can just drop the bases and set the exponents equal to each other and do the algebra to solve. And here the algebra to solve is just to divide by negative 1. And that will give me an answer of x equal to negative 3. To check it on this calculator, I've got parentheses to make sure that 1/3 to the negative 3 power is equal to 27. On this calculator, I'd have to enter it like this: 1 divided by 3, exponent negative 3, using the negative on the bottom row of the calculator. And that shows me that when I plug in the number that I think is the answer, I get a true statement. This calculator is so much better because I could do a math, arrow over the fraction. Well, I probably should do a parentheses first. Left parentheses, math, arrow over the fraction, ND button, and then 1 over 3, arrow out, make a parentheses, up arrow, negative in the bottom row of the calculator, 3, and I get that perfect checking as well. Just harder to see, I think. 8's a sneaky big number to do a prime factoring for. 8, if I look at the digits of 243, if I add 2 plus 4 is 6 plus 3 is 9, because the digits add up to 9, which is a multiple of 3, 243 is divisible by 3. So to figure out the prime factoring, I'm going to divide 243 divided by 3 to figure out 3 times what is 243. And it looks like 3 times 81 is 243. And then 81's a number I know. 81 I could be written as 9 times 9. 9's not prime. I almost incorrectly circled it. And then each of the 9's is 3 times 3. So if I count up, there's 1, 2, 3, 4, 5 3's. So 243 factors into 3 to the 5th power. Now I have both sides written with the same base. So I can drop the bases and set the exponents equal to each other. Notice I stuck a 1 in front of this x. It's just going to help me do the math I need to do, I believe. So this, now I'm going to go 5 to the 5 minus 1x equals 5. And this has a sneaky answer. I'll check it in a second. I'm going to minus 5 from both sides and get minus 1x equals to 0. And then divide both sides by negative 1. On the left side, when I divide by negative 1, I'm left with the x. On the right side, 0 divided by negative 1 is equal to 0. So my answer to this, I think, is 0. For checking purposes, I should go to see if 3 to the 5 minus 0 power equals to 243. And if I don't want to do anything in my head, I could just enter that on my calculator, if I could actually do it on my calculator, and I'll get a true statement. So every single problem in this section can be checked, so there's no reason to write a single wrong answer for any of the problems in this section. 10 and 12, or 9, 10, 11, and 12, the number that needs the prime factoring already has an exponent, and when that happens, before I do the prime factoring, I need to put this number that's going to get prime factoring in a parentheses, because I'm going to need to multiply the exponents. So because I needed to do a prime factoring for 27, and because 27 already has an exponent, I'm going to put the prime factoring for 27, which I've already done, in a parentheses. And that's how I'm going to start the left-hand side. The right-hand side, I'm going to emphasize that that 3 has an exponent of 1. Now I'm going to clear the parentheses by multiplying the exponents, and this is going to give me 3 to the 3x power equals 3 to the 1. Now that I have the bases the same, I drop the bases and I set the exponents equal to each other, and then divide by 3, divide by 3. I believe the answer is 1/3. I should check right there. And for checking, it should be that 27 to the 1/3 power equals to 3. And I'll just check this. I'll go 27 up arrow. The exponent on this calculator has to be in a parentheses because it's not raising the exponent for me. And this gives me a perfect check that 3 equals to 3. One more of these problems, and then we move on to the problems that I can't solve this way that look remarkably similar. So, need to do a prime factoring in 12 for 49. 49 is 7 times 7. Both of those are prime numbers. So the prime factoring for 49 is going to be 7 to the 2nd power. Because the number that I'm doing the prime factoring for has an exponent, the prime factoring needs to go inside a parentheses. So I can rewrite this as 7 squared to the x power equals 7. The 7 on the right side has an implied exponent of 1. Now I can multiply the exponents to clear the parentheses. This gives me 7 to the 2x equals 7 to the 1st. And now drop the 7, set the exponents equal to each other, and I get an answer of 1/2. I'll check it right up here. Just do 49 exponent 1 divided by 2. Just changing that exponent to 1/2. That's simplifying the left-hand side. It needs to match up with the right-hand side, so I should get 7 when I hit enter, and I do. So 1 through 12, those are problems that we've already done twins to. That's not anything new. Once we get beyond 1 through 12, the next problem's 13 through 24. I can't do this way. If I did a prime factoring, like if I tried to do 14, if I tried to do a prime factoring for 10, well, 10 is 2 times 5, which is fine, but in order to solve this problem using the strategy I did for 1 through 12, I need to be able to write each side with just a single prime numbered base, and I can't with the 10. So these problems I need to solve with logarithms, and I wrote some steps down. For problems 17, 18, 19, 20, there's going to be an additional step that I'll talk about when we get to those. Most of the problems in the 13 through 24 only have the last few steps. And what are my steps? And then when we get to the problems where this makes sense, I'll show you how it makes sense. Right now, it's not going to make sense, this step. So we're going to start with number 2, 3, 4, and 5 until we get to problem 17. Step 1, take the logarithm of both sides. Take the ln of both sides if the base of the log is, if the base is e, and there's no e here. So for 14, I'm going to take the logarithm of both sides. I'm going to go the logarithm of 2 to the x equals the logarithm of 10. Done with step 2, which is my first step here. Next, make any exponent into a coefficient. So I'm using the rule that allows me, if I have a logarithm that has an exponent, to make that exponent into a coefficient. Do the algebra to isolate the x. It's pretty actually easy algebra to isolate the x. To isolate the x, I'm just going to divide both sides by log of 2. This is the best answer. Not such a great answer for checking. This would be a disaster to plug in for x. So I'd call this the best answer. And the instructions say you can round your answer to 2 decimals. I'm going to round to 2 decimals. I'm going to put both in my answer blank. And when I check, I'm going to check the rounded answer. And checking a rounded answer is not going to work perfectly. So in order to do this on a calculator that you might be able to see, I'm going to do log of 10, parentheses, divided by log of 2, parentheses. This would be the same keystrokes on my other calculator as well, unless I wanted to enter it as a fraction. And this is about 3.32. What I'm going to do is check, and the best I can, I'm going to put the exponent in, 3.32, and see if I get a number close to 10. I'm not going to get exactly 10 because I have a rounded answer here. So if I go 2 exponent 3.32, I get 9.98. Notice if I would have put 4 decimals in, if I would have done 2 exponent, and if I rounded my answer to 4 decimals and did 3.3219, I'd get even closer to 10. This is an approximate checking, but it's close enough. I believe that 9.98 is close enough to 10 because I'm putting in a rounded answer that I think my answer is correct. The chances of me getting an answer that's wrong that gets that close to checking when I'm putting a rounded answer in is pretty slim. This word there doesn't belong. I'll have to delete it everywhere. So, problem 15. This is where I see ease. Skipping until I get to problems 17, 18, 19, 20. I'm skipping this step. First step is to take the logarithm of both sides. Take the ln of both sides if the base is e, and here the base is e. So on 16, I'm going to go the ln of e to the x equals the ln of 1.15. Then, that's the end of step 2, which is my first step here. Now I'm going to make the exponent into a coefficient and make x times the ln of e equals the natural log of 1.15. The natural log of e is equal to 1. This is a common thing to come up. If I did natural log and then second and divide, you'll see that the natural log of e is equal to 1. So this is really x times 1 equals the natural log of 1.15. So the best answer, a non-rounded answer, is x equals the natural log of 1.15. Maybe I can put that 1.15 in a parentheses, but it's not necessary. I'm going to get a 2 decimal answer. Do the ln of 1.15. And if I round that to 2 decimals, I get 0.14. I rounded up, so when I check, my answer is probably going to be a little bit over. I claim the ln is the best answer. For checking purposes, the decimal is better. And to check, I should see if e to the 0.14 power is close to 1.15. Because I rounded up, it probably should be a little bit over, but it should be close. How do I do e to a power? I hit my second button and my ln key. And now I type in the answer, 0.14, and I get 1.150, way close enough. I feel good about my answer. So I'm going to say it's right, even though it's not perfectly checked. To check perfectly, I'd have to use that ln, but that's just silly for the calculator. 15, 17, 18, 19, and 20 is where I need to do step 1. Step 1 says isolate the exponential function. It says when needed, divide by the coefficient of the exponential function only needed for 17, 18, 19, and 20. If you look at 17 and 18, at 17, the number 5 is multiplied by the exponential function 10 to the x. On number 18, the number 4 is multiplied by the exponential function 3 to the x. Here, I need to isolate the exponential function by dividing by the coefficient of the exponential function. In 17, you'll divide by 5. In 18, I'll divide by 4. And in 18, when I do that, the left-hand side is going to become 3 to the x. The division makes it so I can drop the parentheses. The right-hand side is going to become 6. Done with the first step, move on to the second step. Take the logarithm of both sides. I don't see an e, so I'm just going to ln both sides. Ln the left side, ln the right side. That's the end of step 2. Step 3, make the exponent into a coefficient. Maybe I'll put some parentheses around my arguments. Should probably be consistent one way or another. I just usually instinctively, if I'm not thinking, I don't put the parentheses. They're not really necessary. Now I'm doing the algebra to isolate the x, and I get the best answer. X is the ln of 6 over the ln of 3. This would be ridiculous to check, so let me get a decimal approximation for ln of 6 divided by ln of 3. I should put my calculator into 2 decimal mode. That's 1.63 rounded. So when I check, I'm going to see a 4 times 3 to the 1.63 power is give or take 24, maybe 23.9, 24.01. So let me check by going 4, parentheses, 3, up arrow, 1.63, close out the parentheses, hit equals, and 23.97, close enough to 24 for me to believe my answer is correct. The real checking would be just ridiculous and take too much time, and it's not. This is good enough. And if I want to get better, I can do more decimals. I can go 4 parentheses 3 up arrow, then take 4 decimals, 1.6309. Instead of rounding to 2 decimals, round to 4 decimals. And look how much closer that is to 24. So if you're not comfortable that your checking is close enough, take more decimals. If you took all the decimals, it would equal exactly. Or I think it will come out exactly, but I'm not going to take the time to do that. So 19 and 20 also have this coefficient. So for 19, I have to do this first step. In 20, I need to do this first step. I need to divide by the coefficient of the exponential function. So I divide both sides by 14. On the left-hand side, the 14s cancel, and I'm left with e to the 3x. On the right-hand side, 42 divided by 14 is 3. Done with my first step. Move on to the second step. Take the logarithm of both sides. Take the ln of both sides if the base is e. So in number 20, because the base here is e, I'm going to take the ln of both sides. Done with the second step. Now make any exponent into a coefficient. This is going to give me 3 to the 3x times the ln of e equals the ln of 3. The reason we do the ln on this problem is because the ln of e is equal to 1. So I can rewrite this as 3x times 1 equals the ln of 3, which gives me 3x equals the ln of 3. And then I could just divide by 3, and get x equals the ln of 3 over 3. That doesn't reduce. The logarithm is kind of like an exponent, and you'd have to simplify it before you can do the division. Let me get a decimal approximation by going ln of 3, close out my parentheses, divide it by 3. And I get 0.37 if I rounded properly. I should have put my calculator in 2 decimal mode. And for checking, I should see a 14 e to the 3 times 0.37 is reasonably close to 42. The more decimals you carry, the better the checking is going to be. But let me check here. So 14, second in ln for my e, and then 3 times 0.37, and I hope I get something close to 42. 42.48, it's pretty far away. Let me check again. 14, second, ln, 3 times, let me carry more decimals, 0.36620400962. Carried all the decimals. Look, it came out exactly. So the more decimals you carry, the better your checking is going to come out. Ugly 2 problems coming up or ugly 4 problems coming up. The first step's not going to apply anymore for the rest of the problems in this grouping. What is going to be is bad, 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 because both sides have an exponent of x, way harder algebra. So on step 2 for problem 22, take the logarithm of both sides. I'm going to the logarithm of 2 to the x equals the logarithm of 3 to the x minus 1. This is really unfortunate that both sides have an x in the exponent. Now I'm going to make both exponents into a coefficient. I'm going to get x times the log of 2 equals to x minus 1 times the log of 3. Ugh, not good, not good, not good, not good. I need to clear this parentheses that I introduced on the right-hand side by going x times the log of 3, which is going to give me x log of 3, and minus 1 times the log of 3, which is going to either give me minus 1 log of 3 or just minus log of 3. There's no x squared, so I need to get the x's on one side, the numbers on the other, and solve by dividing. To get the x's on one side, this is the evil trick to this problem. I'm going to subtract x log of 3 from both sides. And when I do that, I cancel out the x logs of 3's, and on the right-hand side, I just have minus log of 3. On the left-hand side, I get x log of 2 minus x log of 3. I can't have two x's. I need to factor out a common factor of x on the left-hand side to get the left-hand side down to a single x. So I'm going to take this x and this x, factor it out, and I'll be left with log of 2 minus log of 3 inside my parentheses. And now I'm going to finish up my problem by dividing. I have x times some disgusting looking logarithm. I'm going to divide both sides by that complex looking logarithm. And this is my answer that's not rounded at all. The answer is x equals negative log of 3 over log of 2 minus log of 3. Let me figure out what this is. This is a little lifting to get this. So I get negative log of 3. That's the numerator. And then divide it by, and the denominator needs to go in a parentheses. So parentheses, log of 2, close out the parentheses on the logarithm, minus log of 3, close out the parentheses on the logarithm, and then close out the parentheses on the denominator. For 2 decimals, this is approximately 2.71. For checking purposes, I need to put 2.71 in for both x's and make sure both sides come out to about the same number. So the left side is 2 exponent 2.71, which is about 6.54. The right side is 3 exponent parentheses 2.71 minus 1, which is 6.54 rounded to 2 decimals. So my answer is good enough. One more of these. I'm going to go a little bit long on this video so we can get into a part 2 without hopefully having to do a part 3. Let's do 23 together. So 23, both sides I'm going to take the logarithm of. Maybe pause the video and try to do 23 without me. That would be the best thing you can do. So take the logarithm of both sides. I get the logarithm of 6 to the x minus 1 equals the logarithm, base 10 for that matter, of 9 to the x. That's the end of step 1. Step 2, make any exponent a coefficient. So this is going to give me x minus 1 times the log of 6 equals x times the log of 9. I introduced the parentheses on the left-hand side that was necessary. I'm going to clear that parentheses and make the left side x log of 6 minus 1 log of 6. And now I need to get the x's gathered together. And it's best to get the x's on the right-hand side here because I have a constant term on the left-hand side with that minus log 6. When I minus x log 6 from the left side, I'm left with minus log 6. And on the right side, I have x log 9 minus x log 6. Just like I did in the last problem, on the left-hand side, I'm going to pull out my common factor of x and get inside of parentheses log of 9 minus log of 6. Because when you factor out this x and that x, you're left with that and that. Now divide both sides by log of 9 minus log of 6. Divide both sides by log of 9 minus log of 6. On the right-hand side, that disgusting thing cancels. I'm left with an x. And on the right-hand side, I have something that's suitable for an answer, but I best figure out what this equals to decimal-wise. I would never want to check that by hand. So this, what is this equal to? So minus on the bottom row of the calculator, log 6 parentheses, that closes out the numerator, then divided by parentheses to start off my fraction. Log 9, my calculator forces me to have a parentheses around the 9. I need to close it. Minus log 6, my calculator forces me to have a parentheses around the 6. I need to close that parentheses. Then one more parentheses to close the denominator. And the two decimals, this is approximately negative 4.42. So for my checking, it should be the case that 2 to the negative 4.42 power is about 6 to the negative 4.42 minus 3. I'm worried that my answers are going to have e's in them. I might not write down my answer. I'll just glance at them to make sure they look the same. So 2 exponent negative 4.42. Oh, it didn't get that. And on the other side, 6 exponent parentheses negative 4.42 minus 3. Oh, I made a mistake somewhere, huh? 6 to the negative 4. I don't see a mistake. Let me look at my work here. This work is pristine. Log of 6, log of 6, log of 6. That's right. I must have a calculator error here. Let me do this calculator error. So negative log of 6 divided by parentheses log of 9 minus log of 6. Still get that negative 4.42. 2 exponent negative 4.42. The left side is that. 6 exponent negative 4.42 minus 3. Forgot a parentheses here, which is will doom me. 6 exponent negative 4.42 minus 3. I have a mistake. I'd like to stop the video, but I don't want to stop the video at an error. So I have no idea where my mistake is. Unfortunately, this video has to go long. I can't find my mistake. So, idiot. Here I am checking into problem 24. I should be checking into problem 23. That you never get a check if you're checking the wrong problem. So I should be checking here. I should be going 6 exponent parentheses negative 4.42 minus 1. Checking into the right problem. That gives me something disgusting. And let me do that 9 exponent negative 4.42. And if you look at this 6.05, 6.05 e to the negative 5, these match to two decimals with the same e. I'm going to say those check just fine. So I was dooming myself because I was rushing, and when I rush, I make mistakes. It's a good habit to not rush because it's dangerous to rush. So we're going to move on and do a part 2, possibly a part 3, but I hope not a part 3.